In this chapter, we will be introducing the concept of integration. In this lesson, we will be looking at the fundamental theorem of calculus.
All right, hi everybody. So here we are. Now we're going to look at the fundamental theorem of calculus. So, we've come a long way in this course to get to the fundamental theorem of calculus. But what this is really is it's just a statement of the relationship between those two branches of calculus that we talked about last video here. And so there's really nothing new going to be said here. In fact, this is going to be just a kind of a summary lesson of the big ideas that we've looked at just recently. And then we'll take a look at some examples. So here's what the fundamental theorem of calculus says. It says if you've got this function little f of x, okay, that's my lowercase f. If f of x is a continuous function, okay, continuity is really important. If it's a continuous function on the closed interval, okay, on the closed interval, and let's make that a to b, okay, and we're going to let capital F of x be defined. So we're going to let capital F of x is defined for all. Now, just so that you know, later on when you do when you all start studying math at university or wherever you're at here, for all is typically going to be symbolized as like this upside down A. Okay, you're going to see that show up here, just so you know what it means here. For all x inside that closed interval a to b, we're going to let f of x be defined as follows. So capital F of x is going to be, we're going to use the integral from a. Now I'm going to go up to x. It's important that you catch that I'm going up to the variable x, okay? So I'm going to put my independent variable up there, and I'm just going to put my lowercase, and this time I'm going to make it f of t dt. Okay, so I'm defining my capital F to be the integral from some constant a to the independent variable, and I'm using t as a different variable for integration here. Now, what this tells us that is then f is continuous on that closed interval a to b, and not only is it continuous, it's differentiable on the open interval a to b, because remember, I really can't define derivatives at endpoints because of the fact that a derivative relies so heavily on limits. Okay, it doesn't work that I can go to endpoints here. And not only that, and here we go, here's the real connective piece here. The derivative with respect to x of capital F of x is going to be lowercase f of x. And this is going to be true for all, okay, remember, for all x in that open interval a to b. Okay, now at this point here, you might look at that and say, wow, okay, well, you might have two responses to it. You might look at it and say, okay, yeah, well, we've seen all that before. Or this might just be a whole bunch of mathematical blah, blah, blah that doesn't mean a whole lot to you. So let me give it to you just in another way of looking at it, okay? So I'm just going to draw a little line here. So another way of saying this, okay, and we'll say it like this. Another way of saying this is that if f of x is continuous on that closed interval AB, then, okay, then let's come down here a little bit. Whoops, sorry, I don't want to lose you there. Then the integral from a to b of f of x dx is simply equal to its antiderivative evaluated at b minus its antiderivative evaluated at a. Okay, where, and although, I mean, we know that to be true because of what we've done in the past with our notation, we know that capital F is the antiderivative of little f. We're just going to state that, where capital of f of x is any antiderivative of little f of x. Okay? And I say any antiderivative because of the arbitrary constant. Now, if you're not entirely sure how I'm getting that, let me just kind of switch colors here and let's talk about this. If we just assume that capital F of x is an antiderivative of little f of x, let's go back up to what this is saying. Okay? The derivative here, f of x, capital F of x, is equal to this right here. And then when we take the derivative of that function, we're going to go back to f of x. So basically what we're saying here is that if you take the derivative of this, okay, the fundamental theorem says that you're going to get little f of x. Okay, let's follow that through. Let's follow through what's going on here. So again, I'm going back up to the original statement of the fundamental theorem of calculus, but I'm going to use this idea that I just came up with just to show you what's going on here. So we know that f of x is supposed to equal the antiderivative from a to x of f of t dt. Now, based on our experience here, we're already should already be somewhat aware of this, that what this means here is I'm going to take the antiderivative of this right here, and that's going to be capital F, and I'm going to evaluate that at x, and then I'm going to subtract that thing evaluated at a. Okay, well that I haven't really said anything because we knew that. I mean, we've already done that in the last couple of videos here. But now watch what happens here. If I now take the derivative of this function with respect to x, okay, that is going to be the derivative with respect to x. Oh, I don't know why I put parentheses around that there. I really don't know what I was thinking. Of the right-hand side. Now, here's the thing. Based on how I've just described this, I know that the relationship between capital F and little f is that capital F is the antiderivative of little f. So I know that the derivative of f here, capital F, is going to be little f. But more importantly right now, I know that this is going to be a constant. Because it's evaluated at a constant, I'm getting rid of my independent variable. I'm replacing it with a value here. So I'm going to get a value there. And when I take the derivative of a constant, that's going to disappear. And so all I'm going to be left with is my little f of x. That, if you combine these two ideas, this fundamental theorem of calculus that we were just introduced to you, and what we know to be true about the way integrals work, that's the relationship that we're seeing. Okay, I hope that makes sense. Now, this is going to lead to a couple of other ideas that we're just going to summarize here in just a second. Okay, so this takes us to the definite integral. And we've already talked about this, right? The definite integral is this little bit right here. It's the integral from a to b. Now, it's important to see those endpoints there of f of x dx. And this is definite integral, okay, and it represents the area or the difference between the areas between the curve and the x-axis over this interval from a to b. Because remember what this is. We're creating this infinite number of rectangles here where f of x represents the height. And remember, that's always going to be measured from the x-axis. So in some cases that could be going up, in some cases it could be going down. And dx represents the width of each one of those rectangles here. Now, just a little note, okay, that when you've got the capital, or the antiderivative of f evaluated at b minus the antiderivative of f evaluated at a, can also be written in different forms here. Okay, I could write that, or I could express that as f of x with a straight line up and down with an a and a b written like that. Okay, or sometimes you'll see capital F of x and then you'll see the little the right hand side of the square brackets there, and again from a to b. You just need to be aware of what that looks like. Okay, just in case your teacher, your professor, whatever, uses different notation, you kind of got to get used to your instructor's notation here. So typically we might write it like this: the integral from a to b of f of x dx, okay, is going to be the antiderivative evaluated between A and B, okay? Where, yeah, capital F primed of x is equal to f of x. And again, that's just saying something that you should already be familiar with. Now, let's just take a look at a quick example here. Whoops, can't see that. Actually, let me zoom out just a little bit here, the other way. Okay, let's just take a look at a quick example here. So if I take the integral from -1 to 5 of 6x minus 7 dx, okay, so what this is going to equal is the antiderivative of this evaluated between those two endpoints, okay? So what is the antiderivative of 6x? Well, I'm going to increase the exponent by 1, divide by the new exponent. So that's going to be 6x squared over 2, or 3x squared. The antiderivative of 7 is just going to be 7x. And remember, there's going to be this arbitrary constant that we have in there. And we're going to evaluate that between -1 and 5. It's just as straightforward as that. So now what I'm going to do is I'm going to evaluate this, okay, at 5. There's my arbitrary constant there. And I'm going to subtract the value when it's evaluated at the low end of my interval, my -1. And when I do that, this is all going to become 40, assuming I did that right on the paper just off to my side here. This is going to become 10, and altogether I'm going to get a value of 30. Okay? Now, is that the area under the curve? Is that the difference between the areas? Well, until you take a look at what that graph looks like, hard to say. But that's the value of that integral. Okay? And that is a definite integral. Okay, so now an indefinite integral, okay, it's going to look like this. And notice what's missing here. I don't have the a and the b specified here. Okay, this is an indefinite integral. And it's indefinite because there is no interval that we're specifying. That's why it's an indefinite integral here. And what it represents is really just the antiderivative of that function right there. It's not an actual value. Okay, it's not an area. It's just the antiderivative of that function. So for example, if we go back up to what we had just looked at here, if I had this written out, which is the integral of 6x minus 7 dx, if there's no limits given, okay, to my integration here, then what this represents here is just the antiderivative of that function. We've already established that was going to be 3x squared minus 7x, and in this case here, I really need to include that plus c. Now in the previous work that I did up here, my c's canceled. And in fact, anytime I was evaluating that between those two limits there, the c was always going to cancel, so I really don't even need to write the c. It's not relevant, it's not affecting my answer. But here, I do need to write the c, okay? Because this isn't being evaluated between two limits, I need to recognize that that's the antiderivative of this function, and that I need to include an arbitrary constant in that answer as well then. Okay, so I'm just going to write down a couple of properties of integrals that I really want you to know here. I'm only going to write down a couple here. First of all, if you've got the integral, and it can be definite or indefinite here, and you've got some sort of constant multiplied by your function here, I can actually just take that constant out and then take the integral of f of x dx and then multiply that by that constant afterwards here, okay? So that's true, where c is a constant. Now on top of that, another property, and by this time here you've very likely already figured this one out. If you've got two functions being added or subtracted, okay, but if they're being combined together by addition or subtraction here, then what you can do here is you can actually split this up, okay, and take their integrals separately, okay? So the integration of a sum or a difference is really the same as the sum or difference of the integrations there, okay? And again, you've probably, based on the examples that we've done, you've probably already pieced that together. Now, one of the things you should know about integration here is that it is generally difficult to do. Okay, and I'm not saying that to be a jerk or to scare anybody off here, and I mean this in a very, very general sense. By this time in this course, you probably can take the derivative of all sorts of things, like just almost anything I could throw at you, you could take the derivative of. You've got the tools for that. The thing is, you can't easily take the antiderivative of anything. In fact, it can be very difficult to figure out how to take the antiderivative of an expression. In fact, in some cases, the only reason we know what an antiderivative should look like is because we recognize a derivative that we took. Okay? And so what you're going to see as you progress through this, there's going to be a lot of different procedures that you're going to encounter that are designed to help you take the antiderivative of an expression when it looks in a certain form. Other things that you might be directed to do here is simply look up the expression that you've got in a table. There are whole books dedicated to this where you'll see all sorts of integrals and what their answers are supposed to be. In fact, in the textbook that you're probably working with right now, sometimes it's at the front of in the front cover, sometimes the back cover, but there's usually a table of integrals, and you're encouraged to look for the form of the question that you've got in that table, and it'll tell you what the antiderivative is. It can be quite complicated. Anyways, let's take a look at some examples. Okay, so this one right here, first of all, I notice that it is a definite integral. So I'm going to get a result here. I'm going to get an answer. I'm going to rewrite this though, because I don't like the look of that radical in the denominator. So I am going to make this 2 x to the negative 1/3 dx. That's a little bit easier for me to work with. Now, in addition to that, I'm going to apply one of the properties that I've just looked at. I'm going to bring that 2 out. This will be the integral from 1 to 27 of x to the negative 1/3 dx. Okay? And so now what I'm going to do is I am going to increase my exponent by 1, okay, and divide by that new exponent. Now I've still got this 2 hanging outside here, so this is going to end up being x to the 2/3 divided by 2/3, and that is going to be evaluated between 1 and 27. Now, normally I would think to put a plus c in there, but because this is a definite integral, I know that plus c is irrelevant, so I'm not even going to write it. Don't just take that as a general statement of the way you can do these things. You've got to determine what your teacher wants you to write, okay, what your instructor is expecting from you. So you might be expected to put that plus c in there all the time. You got to figure that out for yourself here. So now, when I put this together, I'm dividing by this 2/3. So I'm going to multiply by the reciprocal. My 2's will cancel, so that is going to be 3 multiplied by x to the 2/3 from 1 to 27. So now I know that this is going to be 3 multiplied by 27 to the 2/3 minus 3 times 1 to the 2/3. Okay, well this should actually come together fairly nicely for me because the cube root of 27 is 3. Squared is 9. Multiplied by 3 is 27. Here, 1 to the 2/3 is just going to be 1. And so if I subtract 3, 27 minus 3, that is going to be 24. Okay, in this question, I notice right off the bat that this is an indefinite integral, so I'm going to have a plus c at the end here. There's no limits. What I'm going to do here, though, is I'm going to split this up into two different integrals. So this will be the integral of 3 over x minus 1 dx plus the integral of the cosine of 2x dx. Okay, now I can pull that 3 out and really treat this as 3 multiplied by the integral of 1 over x minus 1 dx plus the integral of the cosine of 2x dx. And now, having a good look at this here, I recognize that pattern, the 1 over the x minus 1. That is the natural logarithm. So this is going to be 3 multiplied by the natural logarithm. And remember, I'm going to put absolute values around that, x minus 1. And again, I put the absolute values around that because here, the domain of this function is x can be anything but 1. If you don't put the absolute values around this, then the domain of your natural log is going to be x has got to be greater than 1. And so those two functions don't match up in terms of the domain, but when I put the absolute values around them, yes, they do now. Now, here, I got to think about this a little bit. Okay, I've got a cosine, and I know that the derivative of sine is going to be cosine. I know that. So I know that the derivative of sine of 2x will be the cosine of 2x, except that if you take the derivative of this, I would then need to multiply by the derivative of the argument there, the 2x. So that means that the derivative of the sine of 2x would actually be 2 cosine of 2x. But, well, there's no 2 here. There's no 2 here. So for some reason, the 2 disappears. And the reason for that is because of a half that's multiplied in there as a coefficient. And so that is going to take care of that for me. So now at the end here, I'm just going to throw in an arbitrary constant to finish that expression off. All right, let's just do one more question here. And when you take a look at this one, again, notice that it's an indefinite integral. I'm going to end up with an arbitrary constant at the end. I really don't like the way that looks when I look at it here, this rational, but I can simplify this a little bit here. So I'm going to rewrite this rational, and what I'm going to do is I'm going to distribute that monomial denominator to the 3 terms in the numerator. So t squared over t will just be t plus, now the root of t divided by t, this is going to be t to the 1/2 divided by t to the 1. So when I subtract the exponents, the positive 1/2 up here, subtract the 1 that I'm getting from down here, that's going to be t to the negative 1/2. And then there's not much I can do about this. This is going to be 2 divided by t. That is as nice as that's going to get. Okay. But now I can go through and I can integrate this term by term. Okay. This first one is going to become t squared over 2. This one right here, I am going to increase the exponent by 1. So it's going to be t to the positive 1/2 divided by 1/2 is going to be the same as multiplying by 2. So 2t to the 1/2. Now it's an interesting comparison between those two here, right? This goes to positive 2. I divide by positive 2. This goes to positive 1/2. I'm dividing by 1/2, and it's the same as multiplying by that 2 there. In this last term, I see the t in the denominator to a 1. And again, I recognize that immediately as being the natural log. And so I put my absolute values around there. The 2 is just a coefficient I pull out. And then I have this plus c at the end there. Now, that is my answer. That's good. That's totally fine. I'm going to go one step further here just to show you what you can do here. There's really not much you can do here. T squared over 2, that's fine. Plus 2t to the 1/2, that's fine. But one of the things here I can do is I can move that square up as an exponent, and that's actually going to deal with the absolute values there, because as soon as you put the 2 up there and you square the value, a square can only be 0 or a positive value, and so that actually covers it for me. Okay, that does basically, or deals with basically what that absolute value there is dealing with at this step. Thanks.